And I'm pleased to invite Hagai Perets to talk about the region of
Type 1a supernovae.
oh, okay.
Story of paradigm lost.
Hagai got his PhD in Vaidman Institute, and then he got prestigious postdoc in Harvard. And from Harvard, he went in Technion, and now he's a professor in Technion. And you are welcome.
Thank you very much. So, as always in colloquia, I try to aim for all levels of the audience. So I'll try to keep as much as possible of the audience together with me throughout the colloquium. Let's see how I'll see. What I want to do today is to tell you a story. And why is that? Because my father is a storyteller. And I always like to tell stories like he does. And I'm going to tell you about the origins of supernovae. So this is just the acronym. Supernovae, the explosions or the end of life for stars. And it's really a story of various paradigms, scientific paradigms, lost over the eons, basically. So let's begin. But before that, I should, of course, important is that, of course, I have many collaborators. Most important is Yosef Zinati, my former PhD student, now a Perets fellow in Johns Hopkins, who was really responsible for most of the actual work that was done here, but also the other collaborators. So let us begin. So my father told me that every good story, really the best stories, have several aspects of them. And they have these components: surprise, religion, royalty, sex, and mystery. Of course, not all stories have them, but some of them do have them. And I would like to give you an example. Short story. Oh my God! Okay, so which part is that? Surprise and religion. Okay? Yeah, for some of you, maybe the sex too, but so, oh my God, said the princess. Princess, royalty. I'm pregnant. Why not sex? But I don't know from whom. Mystery. So this just to exemplify kind of these various components. So in my story, I'm going to try to give you, at least try to get most of these components. So we have religion, well, in some sense, the science versus the church. So I'll discuss a bit of that. We have royalty, which is, the scientific counterparts are Nobel laureates. Sex, well, okay, not exactly, but when two white dwarfs, and I'll tell you about white dwarfs, when they come intimately close, there's a lot of fireworks, so, okay? And mystery and surprise, so that's all science is all about. So, that's up to you. Actually, there are various different ones, and so I'm really going to mostly focus on so-called thermonuclear supernovae, but I'll try to start the story with the general issue of supernovae and what they are, because in the beginning we didn't understand what they are, or there are different types of supernovae. So let's start. So imagine yourself like 2,000 years ago. You're going outside, no light pollution, the sky is amazing, you can see all the stars. And really, at that time, people really knew their stars. And like I say here, okay, I know the passes of the sky like the passes of my hometown. This is one of the rabbis studied in Babylonian time, and not Babylonian times, but in Babylon. And you look in the sky, and you know the sky, you know the stars. And sometimes you see a new star. You've never seen it, and you know the stars. So when you see a new one, you know it wasn't there. So in some sense, that's the beginning of the research of supernovae. People just saw a new star appearing in the sky. They didn't know what it is, but they just discussed it and mentioned it. And discussed it over the ages. And indeed, the first to actually really record all of these were mostly the Chinese, but also in the Romans, because these were very important because they considered the celestial sky to tell you something about the future and what should you do about it, and to kind of give some counsel to the emperor or whatever. So they really recorded, when each time they saw this new phenomenon in the sky, they recorded and where they are in the sky. And indeed, even today, we can see evidence for this. And what I tell here, why we have supernova 185 is basically supernova which happened at 185. Okay, and going forward in time. So you can see the first one was about 185 recorded, and I say no, some of them were actually found, okay? And some of them, I'll tell you a bit about supernova remnants, but interesting ones were, for example, in 1006, we saw a supernova in the sky which was so bright, it was like quarter of a moon in terms of brightness. You could actually read, during night, you can read just the light by the light of that supernova. And actually you can see it as a star in the sky during the day, it was so bright. So this was one, and that was of course recorded both by the Chinese and the Romans. Very interestingly, in 1054, the Chinese recorded another one, but the Romans didn't. Maybe there were or at least the Europeans did not mention it, and maybe they had too many wars at the time. It's not very clear. They did not look at the sky. They should have seen it too. And then the more modern one were observed in details by Tycho and later Kepler. These are very well known supernovae, and they actually, Tycho termed the term stella nova. Stella, star, nova, new star. So basically, a nova is just how they got the term supernova. Is starting from that, from a nova, just a new star in the sky. And all this already, in some sense, this is the first paradigm I want to break in this talk. And that was the paradigm, the Aristotelian paradigm of an immutable heaven. What do I mean by that? So, Aristotle time, or even later on, they thought about the Earth in the center of the universe. Then, of course, they have the moon, Mercury, Venus, the sun, etc. In the outside, this kind of last circle was just the immutable sky. The stars don't change at all. And that was the belief that the stars cannot really change. But when you see a stellar nova, a new star, they actually change. So in some sense, it already starts to break this basic paradigm of Aristotelian one, which then the church took. So think about later about Galileo Galilei and Copernicus, about kind of all the issues they have with the church. It's already started with that. In some aspects, with already using astrophysical observation. So we begin our journey. At this point, we have very simple classification for novae. Supernovae, just called novae. That's new stars in the sky. It's going to be complicated, so please follow. So we're now going to go to supernovae. And that was actually, this term was actually termed much later on. But before that, I should mention that these old supernovae can actually be observed today as supernova remnants. Because these, today, are stars exploded. The material still keeps on going forward with very high velocity. And you can watch the places in the sky where people recorded the position. You watch these telescopes. These are actually X-ray telescopes. These are not real colors, but they translate it to things we can see. And you can see the supernova remnants. And for each one of these recorded supernovae, you can now look in the sky, but actually not for all of them. Some of the recorded ones we didn't find. Maybe the position wasn't right. Maybe this was a supernova, but something else, maybe even a comet. Could be very many things, but many of them we actually did find in many years later on. So the modern era started around 19th century. You can actually started looking on supernovae with telescopes. And already then, they played a major role in the evolution of science. For example, the first supernova in the modern era, called supernova 1885A, or S Andromeda, happened in Andromeda Galaxy. But you should understand that at the time, we didn't know about galaxies. It wasn't clear. We thought the galaxy is the only galaxy we have. We have an island universe. We don't have other galaxies. So people saw this kind of new star in the sky, but where did it appear? It appeared in a very unique place. Okay, it's Andromeda. And if you look at the sky, it looks like kind of a fudgy thing there. And people thought that was maybe just kind of a strange cloud, astrophysical cloud, something like that. But others claimed that this was actually other galaxies, other island universes. And there was a big debate, cosmological debate, about whether the universe is only our galaxy or do we have other galaxies. And what people say is that, okay, if you have this explosion or something, if it's in another galaxy, it means that it's extremely far away. If it's extremely far away, it means the brightness that we see right now is huge in the origin, because, right, it's like a candle, you see further away, you see less light. So if it's so bright, but it's much farther out from us, it means that it's much more energetic than we thought. And people say, no, that cannot be. So it has to be in our galaxy. And that kind of stood in the center of this debate, part of the things that were in the center of the debate. And as it turns out, history repeated itself later on with many other astrophysical transients that people debated whether they're coming from our galaxy or from other galaxies. Gamma ray bursts, those people know, or even today, you have fast radio bursts, you have the same debates. Each time you have a new transient in the sky, a new kind of transient, people in the beginning are not sure whether they're coming from the galaxy or from much larger distances, and which means that they are much more energetic. So this already played a kind of a break the paradigm of people who thought we have only our galaxy. People start to understand that we have other galaxies. Continue on, we go into 20th century, and then we go to the first supernovae hunters. So these are most well known is Zwicky. and Buddy and Minkowski, so Zwicky, he was actually starting looking at the sky every night, trying to see if they change, but now with telescopes. And he could find actually, he can compare pictures before and after, and then he could find these new stars in the sky, but now with telescopes, so he could see supernovae for the first time in other galaxies. Andromeda was is very, very close to us, but he could see much further away. And almost to this day, he is the kind of the main discoverer, the single discoverer of supernovae. Since there was one which has a better record, but he discovered just 120 supernovae by himself. Today we have big surveys do it automatically with robots, but at the time that's quite amazing. So he was the first to actually try to look at them, and he called them supernovae because if they're coming from other galaxies, they're so bright, they're not just nova, but supernova. They're extremely bright. So this way, how you get the term supernova. Then Minkowski started to take the spectrum of these new stars in the sky, new explosions. And he found that actually there are two types. One, you can actually look in the spectroscopy. One has no hydrogen in the spectra. The other does contain hydrogen in the spectra. And he calls them type 1 and type 2. So these are the kind of the first thing that we kind of characterizing these explosions in the sky. And he also, Baden noted that they have different distribution in galaxies. So galaxies which look like spiral galaxies, you can see these spiral arms like our own galaxy, can show both types of supernovae. But some galaxies, which are elliptical, which kind of not have no much morphology, just kind of globes, they only show these type 1 supernovae. So it's not very clear what they are, but that was the beginning of this whole story. So now we start getting complicated. We have type 1 and type 2 supernovae. Good. We can continue. And then Zwicky already suggested, already in the 20s, a first model for supernova explosion. He suggested that in stars, usually stars burn hydrogen and helium in their core, and then they burn higher element. At some point, they cannot burn the elements. They don't have any heating source in the center, and if they are massive enough, they can collapse. When they collapse, he suggested that electrons can go into the protons and form neutrons, and form a whole star just made of neutrons. Now, you need to realize how crazy this idea was, because just a year before, they actually discovered that neutrons exist. And he now suggested you have a whole star just made of neutrons. Crazy stuff. So Zwicky suggested crazy ideas all the time. Okay? He suggested the existence of dark matter, for example. He suggested you can do lensing with use gravitational lensing. Crazy ideas. About 95% of them were found to be true. Okay? But they are always crazy. And the last 5%, it's probably going to be true, but we're going to discover it later on. Anyway, but Zwicky was a very interesting person, but that's another whole story.
This suggestion was also made at the same time by Landau, by Oppenheimer independently.
That's important because actually for any physical discovery or idea, as you find out, some Russian guy did it 30 years ago, okay, before that.
Landau,
in this case, it's the same time.
Landau is not some Russian
I know. I'm just joking, of course. Okay, I'm just joking. Sorry, I really, I'm just joking. Okay. So, Landau has the respect of all of us. So he suggested the existence of neutrons are already there, but only in the age of the 60s or 70s, this was found by Jocelyn Bell and her advisor Anthony Ilish, who actually looked at the sky in the radio telescope and find these pulsars, which are these blipping objects in the radio. I'm not going into that, but they realized in the end that these are not yellow, green, some kind of extraterrestrial or something like that, but actually pulsars. And as you might know, Ilish got the Nobel Prize for that, together with Rai, who also worked on radio observation. He didn't get Nobel for neutron stars, but for something else. But Jocelyn Bell did not get it. And of course, sometimes people call her Jocelyn Nobel, because she did not get the Nobel Prize. But that's the beginning of another story I told you about royalty. So she did not get the Nobel Prize, but her advisor did get it. Let's continue. So a few years later, by the way, we just diverse aside, Halls and Taylor found a neutron star or pulsar, which actually changed the timing of when the pulsar arrives. And here they realized that you have actually a companion star, white dwarf, and that actually the change in the period of this pulsar tells you that the orbit actually changed with time. And why does it change? Turns out it changed because you have gravitational waves that emit radiation, and actually they and use the energy of the orbit, and they go closer and closer, so the orbit becomes faster. And you need pulsars that are extremely accurate in order to measure it. And they measure it, and for the first time, you actually have an indirect evidence for the existence of gravitational waves, which now we actually observe almost directly. And then they got the Nobel Prize for that in 1993. the story says, and this is just a story, is that Hall at the time in 1993 already did not work on astrophysics, but on some plasma. And Taylor got the call that he got the Nobel Prize, and he said, he of course knew all the aspects of Joseph Bell not getting the Nobel at the time. Said, okay, did my student at the time, Hall, get the Nobel Prize? And they said, no, sorry. So he said, no, I'm not taking it if he doesn't get it. So they called Hall too. In the middle of the night, we called him, you got the Nobel Prize. For what? Didn't remember exactly, so I need to go to the basement and find, of course, his thesis on the PhD for what he got the Nobel Prize. This is not a real story, probably, but it's a nice story. But anyway, both the advisor and the student actually got the Nobel Prize. Now, we go back to the supernovae. As it turns out, people started looking at supernovae and started looking at the spectra, and then find out it's actually a bit more complicated. You have in the type 1, you have no hydrogen, but it turns out you also have subtypes. For example, in some cases, you see strong silicon lines, and others you don't see strong silicon lines. More than that, in some cases, you see helium lines, and some cases you don't see. So they call it type 1A, where you have strong silicon lines, but no hydrogen and no helium. And you have type 1B when you have helium, and type 1C when you have no hydrogen and no helium, but you do have a silicon line. It starts to become complicated, as you can understand. You have type 2, of course, you have hydrogen. So what people realize is that these ones on the right, okay, are coming from co-collapsed supernovae. What are co-collapsed supernovae? Sorry, wait a second. And people suggested these are coming from what Rickett suggested originally. Massive stars just collapse and form a neutron star, and the material just bounces back in some sense and produces this huge explosion. And since massive stars have a lot of hydrogen, you see hydrogen there. And later on, you realize that type 1B and type 1C also do not have hydrogen, but do have helium. Some of them are also coming probably from a co-collapsed supernova. So let's continue. So one interesting thing when people started looking on supernova is that they start having suggestion of various models, for example. So Fowler and Hoyler in the 1960s suggested you have not just a co-collapse, you have another kind of supernova, thermonuclear supernova. Instead of a collapse of a massive star, you have a star which is called a white dwarf. The end of, for example, our star would become a white dwarf when you shed your outer envelope, and what keeps the pressure against collapse of gravity is now the degenerate pressure of electrons. And these are white dwarfs. These are stars made of basically degenerate matter, degenerate electrons. And what they suggested is that, in principle, if you actually put more and more mass on these white dwarfs, at some point, the degenerate matter, you grow and grow and grow. At some point, you become unstable. Why do you become unstable? Think about stars. Let's say I change the density in star or the temperature. If it's higher density in temperature, the nuclear interaction would become much, much faster because they are very, very sensitive to temperature and density. So you start having much more heating, much faster. You hit the star, but then the star hits, so it expands and cools down. And you can do the other way around. So stars are basically kind of a thermostat. You can just stay exactly the same condition. But white dwarfs are made of degenerate matter. Let's say you have some fluctuation, you have some higher temperature density, then nuclear interaction become much, much faster. They increase, but the degenerate matter doesn't expand so much. So you don't really cool down. But now you increase the temperature, so the thermonuclear interaction become even faster. And it goes on, so you have a runaway process. Each time you heat up, you make even more heat. You heat up, you make even more heat, until you have enough energy to actually explode the whole light. That's the basic idea behind this thermonuclear supernova. So what was understood at the time is that stars actually make the elements inside them. And how does good kind of higher elements like iron gets to where we are, or you are made of relatively massive elements, right? They, for example, stars that explode shed their material all over the place, and then later that forms stars and forms the planet and form, in the end, us. In a sense, we are stardust in the most literal sense, make it mainly supernova. That's not another paradigm lost in a sense, because people in the past thought that all the material just formed as it is in the beginning of the universe. Therefore, we realize that hydrogen and helium was produced very, very early in the first sub-second time of the universe, but all the rest was basically maybe stars and exploded in supernova. And they actually got this Nobel Prize. Those guys, the Chandrasekhar and Fowler. Chandrasekhar worked on many, many things you might know, but also about white dwarfs and compact objects. And Fowler was also responsible for understanding stellar evolution and formation of the elements. So when you think about thermonuclear explosion, you can think about the following. Okay, you can actually divide the two. When you put hydrogen and hydrogen together, okay, you made a helium, and then you can actually increase it, add more and more elements, fuse them together, And each time you can actually get energy. So you need to put some energy in order to put them together and make a higher element, but you get much more energy than you put in. Okay, so that's in the first part until you get to iron. Iron is very, very stable. Actually, if you need to actually put more energy than you get if you actually want to get higher elements by fusion. What you can do is the other way around. If you have very, very massive, very, very large elements like uranium, you can actually split them and get the energy. So if you go this side, you get energy. If you go this side, you get energy. So the basic of fusion is how stars work, but also how explosion, thermonuclear explosion effectively work. Core collapse supernovae are somewhat, in some sense, related to this other process, but I won't talk about those. Let's continue. At this point, we have more and more observation, 50s, 60s, 70s. We start to understand that all this right side of one, we know this is core collapse supernovae type 2. People start to divide them to how they evolve with time. See, the light changes. It goes higher and then goes down, but in what structure does it go there? What kind of strange spectra does it have? So we start to divide it. It's kind of a zoology of all these different types of supernovae. And now we have all these sides. And these are, so people realize all these are core collapse supernovae. And people at that point thought that, what is this side, this other side? People suggested these are thermonuclear supernovae. And why is that? If thermonuclear supernovae are coming from white dwarfs are stars, they're kind of late times of stars, so they only exist at very old times, relatively old times. I told you about these different types of galaxies. So those that are only type 1As are found in some of them are old galaxies. So they couldn't have stars that are very massive. Why is that? Massive stars have short lifetime. So if you see massive stars in a galaxy, it means that they just form relatively on a short time scale by millions of years. But if it's an old galaxy, we have no star formation, it means they have only old stars, and you see these explosions there, it couldn't come from massive stars. So they have to come from this explosion, thermonuclear explosion of a white dwarf. Okay, so thermonuclear explosion I just told you about, what you actually get. You get a carbon-oxygen white dwarf. Our star would also become a carbon-oxygen white dwarf. It would shed all the material, left with only carbon and oxygen, about 0.6 the mass of the sun in carbon and oxygen, in degenerate matter, as I told you about. And this would allow, this goes against gravity, this is how it's held together. How you can actually then become unstable and start a thermonuclear explosion, because now it was steady, right? It was very stable. The idea is that if you actually accumulate more and more mass, or you Chandrasekhar tells, you can have a relation between the mass of a white dwarf and its radius. The more massive the white dwarf, its radius becomes smaller and smaller, which means that the density becomes higher and higher. So at some point, you actually go to zero in principle, okay? Of course, you cannot get to zero, so before you get to zero, you get to very high density, and even a small fluctuation in density can start this, or high temperatures can start this thermonuclear explosion. And this is why it happens close to the so-called Chandrasekhar mass. It's about 1.4 times the mass of the sun. If you get a white dwarf to this level, to this mass, you can actually get this thermonuclear explosion. So the question is then, how do you actually get it to this mass, for example? That was one idea. So how do you actually start this thermonuclear explosion to begin? And many of the models I'm going to tell you about are related to this exact question. How do you actually get to this mass? By the way, I'm talking fast. Feel free to, of course, stop me at any given time and ask questions. And the best questions are the ones that seems idiotic, but they're not really. So please do that. So I told you about, of course, already about Chandrasekhar, so we'll continue with that. So it's also important to understand that supernovae form all these intermediate elements. If you actually look on stars, they can actually form the stars that are very massive. They can form all the elements up to iron. But these are very massive stars. You cannot form all of them. You cannot form enough iron, for example, in these massive stars. But it turns out that these white dwarfs, when they explode, they do produce a lot of iron. Why is that? You have very, very dense material, okay? And then you start an explosion. And you can see these kind of rising bubbles, which look like kind of an atomic bomb, because they are atomic bombs, effectively, okay? So you have these bubbles going, these are burning fronts. So you start an ignition, it starts burning, and the burning front just goes through the start. It's very high temperature density, the front, and what does it mean by burning? Burning is making hydrogen or carbon and oxygen into higher and higher elements until you get to iron. Or actually, you get to nickel 56, which is a radioactive element that decays and forms cobalt, which then decays and forms stable iron. So this is how you form. Basically, you stop at iron. So if you have very high density and this burning front goes very, very fast, so before the material knows that a shock is coming, it's already burned. So if it's burned at very high density, it burns all the way to iron. So in principle, you should burn a white dwarf all the way to iron and get only iron, and not the intermediate element that form us. So we are very lucky that this does not happen. Most of the cases, it only burns a bit of it to iron, but the rest is intermediate elements. Why is that? The idea is that you have sometimes the burning is either slower, because you start slow and then it becomes faster. If it's slower, then it starts heating the white dwarf. The white dwarf become a bit non-degenerate, start to actually do expand a bit. The density go down, and when the burning front gets there, the densities are lower. It's not as efficient. It doesn't burn everything all the way to iron. Okay? So that's one of the ways you can do it. Or if you could explode a lower mass white dwarf, which also have lower density, then also you would not burn everything to iron. So it's very important supernova would not be too successful, not burn everything in order to form all these intermediate elements that we see around. Okay? So that's the basic idea of a supernova explosion of white dwarf. But it's just the basic. In practice, people don't really not yet understand it. It's what I'll tell you later on. Oh, that's a good question. And people actually discuss it a lot, and that's related on the model, how you started in the ignition and what cases. So in some models, it's very, very spherical, okay? But in some cases, it's not. Observationally, we can see whether something is spherical or not use superpolarization. The polarization of type 1a supernovae tells us they are extremely spherical in general. Okay, so but that's observation. Why is that? That's an important question. So if you look on the luminosity, this is the luminosity of a supernova, a typical one. So the typical times is like a few tens of days or almost a year. And the reason behind it is that most of it is driven basically by decay of radioactive elements. The explosion itself takes like a second. But then you have to form all this radioactive material. This whole bubble of material, of exploding material, gets larger and larger. The photons start to go out, and as they go faster and faster, they actually can diffuse out and become less dense. And then they just flow out immediately. So, and in the end, you can just see the material, just radioactive decay directly, in a sense. So you produce positons that annihilate with electrons, and you produce photons. And in the end, the late stages are just the exponential decay of actually nickel to cobalt, which takes about 6 days, and cobalt to iron, which takes about 70 days. So what determines the time scale is basically this 70 days time scale of this decay, radioactive decay. So these are typically how supernova look like. They go up very, very fast, and then go slow down, and then they go kind of exponentially down because of this radioactive decay. And you might have heard that, of course, these supernovae, type 1a supernovae, turns out they actually look very, very similar to each other. Not exactly, but they have a relation between the width, how long they take to rise and go down, and the peak luminosity. So why is that important? Because you can use them to measure distances in space. If you had a candle that you know how much light you get from it, if you get further and further out, we discussed it briefly about supernova 1885A, you get less and less light. So in a sense, if you know what you had in the beginning, you can measure and you can know what's the distance. So people actually use supernovae as standard candle. They know that if they see that it goes up and down in some time, they know that the peak luminosity was that. They measure, we know what we measure here, so we can know the distance. So people use it to measure cosmological distances, and this was actually used to measure the most fundamental parameters of the universe, one of the ways. So it's an ugly way. That's phenomenal. You don't even know, don't even understand what are supernovae, you just use them, but it's very, very helpful, and you can actually get the measurement of the universe, and people use it in a sense to measure the acceleration of the universe, and you actually realize that not only that the universe accelerates, the universe expands, but it also accelerates. And that was effectively discovered by two groups. One is in Harvard, Kirchner's group, and the other one is in Berkeley, a Perlmutter group. And Rees and Schmidt were the postdoc, and Schmidt was postdoc, and Rees was a PhD student who actually worked on that in this group. And Nobel Prize only gives three, okay? 3 names in Nobel Prize. You cannot get more, so you have 4 names, but only 3 could get in. So now you get Perlmutter, that's one group. The other one, only Rees and Schmidt. So now you get the student postdoc, but you do not get the advisor. You can realize that Kirchner, talked with him a lot about that, was not happy about that, but you can see the change in attitude. Of course, it depends about what actually contribution you have. It's a lot of interesting scientific politics, which I won't get into, but that's a supernova 2012. So let's go back to type 1a supernova. So they are very important. Why? Because they produce most of the iron elements and large fraction of the intermediate elements in the universe, including material that we are made of. They serve as these standard candles to measure cosmological distance. They actually also play important aspects of feedback in galaxies, which I won't get into much into. So while we go back to supernova jungle. Why I call it jungle? Because before that it was only a zoo and you have all these coconuts. But you can see that at least the left side was actually much nicer. Type 1a supernovae, all of them are the same. Obviously, this is not the case. And then people start finding that they have types, subtypes. Some of them are more luminous, some of them are faint, some of them go slow, some of them go fast. They don't look all the same, and you can actually divide into subgroups. So the zoology continues, and now usually they call it for the first one that they discovered or characterized. So that's kind of present a group. So you have 91Bg-like, 91T-like, etc. You have many, many types of supernovae. So now we have a jungle of supernovae also on the left side. And I told you about jungle, these are not just rare events. If you actually take all the numbers, okay, of these various types of strange supernovae, you don't need to remember or understand all of them, is that about 50% or so are so-called normal type 1a supernovae. Those actually also use as standard candles, and they look very similar in some sense. But all the rest are, you kind of can divide them between various different types, maybe 6, 7 various subtypes of various levels, tens of percent to a few percent, and all of them are different in some sense. Okay, but you can actually find many of those in this group. So these are not just single supernovae, but really a whole subtype of supernovae. And you want to actually really understand not just a normal type 1a supernovae, but all of them in order to understand all the important things I just told you about. And so this is what I told you about, sorry, this is about the percentage. You see the standard about 50%. Of course, there are many selection biases. It's difficult to know exactly, but in general, the non-normal or non-standard supernovae take a significant part of this phase space supernova. And more than that, they also appear in different types of galaxies. So I told you how important it was to understand which galaxies you see different types of supernovae because they tell you something about the progenitors, whether they are massive stars or these white dwarfs. So if you look on these various types of supernovae, you see that, and this is various galaxy types, and see the fraction, and you can see they actually have different cumulative distribution. It's basically different distribution in different galaxies. How many of them explode in this kind of galaxy and other galaxies, spiral galaxies versus elliptical, etc. So we said that it suggests that they form in some sense in a different manner. Okay, somehow they don't all form in the same way. More than that, you can actually also see if you can. It's kind of like the Hertzog-Russell diagrams of the supernovae. Basically, how to characterize different supernovae. You can look on the kind of the magnitude, basically the luminosity, versus the delta M15, which just tells you about more or less the width. How long does it take them to go down? Basically, how many different magnitudes did they go down to in 15 days? This is what I call delta M15. Doesn't matter, it's basically the time scale for this supernova. So you can see that in this measure, you can have this kind of a line, okay, this black line for the Phillips relation. This was actually used in sense of to understand standardized type 1a supernovae. Since you know the relation between the time scale and the brightness that I told you about, you can actually use them using this scale. But now we can see that you have various different types, which are actually not on the Phillips relation, on all over the place. So these are all these peculiar supernovae of different types. So what are the origins of type 1a supernovae? I told you about it's generally understood that these are some kind of a white dwarf explosion. But how does it explode? So you have the two major ideas. The idea is actually to get more mass into the white dwarf, because a single white dwarf is low mass, doesn't just explode. So either you merge two white dwarfs, that's the basic idea. This is called the double degenerate, right? Because you have one degenerate star and another degenerate star, both of them in spiral because of gravitational wave in the end, and emerge, and then you explode in some sense. The other idea is you have a single white dwarf, but you have another star. This star sheds material. This material is accreted on the white dwarf. It's burned slowly, not in the explosion, burns, and then the mass of the white dwarf grows and grows until it gets close to Chandra-Sekhar mass, and then it explodes. So that's called the single degenerate, because they have only one white dwarf. So now the question is, okay, how do you can actually explain all of these supernovae? So we can have it with white dwarf plus a white dwarf, WD is white dwarf. You have different kind of white dwarfs, with different composition. You have carbon-oxygen white dwarfs, more massive ones are called oxygen-neon white dwarf, less massive ones are called helium white dwarf. They have different composition, and I'll get back to that. And in the single degenerate, you can have different types of stars that accrete on the white dwarf. I won't have time to talk about all of them. I will actually focus mostly on the left side, but we'll get to that. Sorry, went the wrong way. Okay, so what is a good model of type 1a supernovae? Okay, what can explain type of supernovae? Every good model needs, in the end, physics, be consistent with the observation. Of course, be able to predict them, and of course, explain everything we already know about. So what does that contain? Many, many things. I won't go into most of them, but you have the composition, the structure, basically, of the explosion, which we can see from the spectra, from the change in the light curve, okay, the evolution of the light curve, polarization, as just mentioned about sphericity. You have different luminosities, different energetics, how much nickel mass do you have there, what's the overall composition, you can learn from the spectra. You have the rates. Different types of supernovae or these peculiar supernovae have different rates. A good model should be able to explain why you have more of this and less of that. You need to understand the delay time distribution, something Danny Morse worked a lot on that. This is basically tell you form a star, how long afterward you would have a supernova explosion. In some sense, it's kind of the green function, okay, of the history of when it exploded. You put a delta function of star formation, and you can have distribution of when do they explode. So every different type of supernovae has a different delay time distribution. When do they explode after the original star form? So we need to explain all this diversity of different types of supernovae, and you also have global composition constraints. We know how much iron we have in the universe. The total of all the supernovae should be able to explain all the composition. So that's a kind of a global constraint. And you have all this aspect of physical aspects of you can actually get in your simulations or model, do all the things that you need to explode, including aspects like successful ignition of the explosion itself, which are not always easy to really even resolve in models. So I probably I'll go pretty fast on that. I won't go into all this, but we have a wide variety of different models of how these two white dwarfs can come together. They can merge slowly because of gravitational waves. They can collide directly if they're perturbed by another component. You can have some accretion, which would lead to a detonation, which I'll tell you a bit about models. But then we have different types of models. I won't go into all of them. What I'm going to tell you is that I'm going to, as I said, mostly focus on this side, on these two white dwarfs. And I won't have time, but you can ask me later on about the other side and what does it have in the sense of the whole picture of supernovae. It does have an important part in the picture, but not for the most of the supernovae that I'm going to talk about. So in the double degenerate, as I told you, there are several models. One of them is the idea that you do the following. It somewhat remind you of maybe of single degenerate. You have a white dwarf and a white dwarf, they come together, but then one white dwarf start to store material before it kind of disrupts completely, start to store material on the second end. Now, the interesting thing is what it happens if it stores the helium. Okay, why helium is important? The higher you go up in elements, the threshold, the temperature threshold intensity, in order to ignite it, to start this kind of fast burning, becomes higher and higher. It's much easier to burn helium than to burn carbon monoxide. So if you have helium, you potentially can explode it on much more easily. So if there's material like helium coming on and accreting, you can actually start to detonate it in much lower temperature. If you detonate it, explodes, and if you have even a small amount of helium, it explodes, but then it can shock the white dwarf, compress it a bit to the shock wave, and then actually even the carbon oxygen white dwarf could explode because of it was shocked by the first explosion. So these kind of models are called double detonation. We have first a detonation of helium, which is much easier, lower temperature, and that induces the second explosion in the carbon and oxygen, which is again a more difficult usually. So some of the ideas are that in this case you have a white dwarf accrete some material, it forms this second double detonation, the white dwarf explodes, and the other companion, by the way, is still left intact, okay, in this case. Other models, you have mergers. So we have both of them coming together. One of them is actually disrupts, and they actually come together, become a more massive white dwarf, and then they explode when they become very massive. And others, which have direct collision, I said, if there's some dynamical perturbation that throw them into each other, not slowly through kind of this slow process, but immediately. In the end, okay, none of these models effectively work. Okay, and this is what I'm going to tell you. And people even try different types of white dwarf. You can have all the combination of different white dwarfs, helium, carbon, each one of them you can put together. It's not really true. Okay, of course I'm cheating a bit. If you actually take very massive white dwarfs, one solar mass and one more solar mass, and you merge them, they do seem to explode very robustly, but they produce only the very luminous supernovae, type 1a supernovae, and these are also very slow supernovae. So they might explain a part of this phase-space explosion, but all the rest just don't explode. If you do lower mass white dwarf, they typically just don't explode. So but in order to understand this, we need to explain about white dwarfs. So I told you we have different types of white dwarfs. This is the mass in solar masses, and this is just kind of the radius. And you can see these low mass white dwarfs, which are much bigger, more puffy. As you go to more and more massive, you change the composition to become carbon oxygen or even oxygen neon in the end. So these are the types of white dwarfs that people usually talk about. And carbon and oxygen neon white dwarf, people understand how they form. You just end the star just burns things in the middle, in the center. At some point, the mass, the pressure from the mass from the outside is not strong enough to continue the burning, and then that it stops. It kind of spools down, the envelope is ejected, and you're left with this generic material. Usually you get carbon oxygen like from our sun, or if you're more massive star, you can even burn all the way to neon and oxygen. Here, in principle, if you actually very low mass star, you don't even burn the helium into higher elements, you're left with a helium core. So in principle, you should see also helium white dwarf. The thing is that low mass stars don't evolve on the lifetime of the universe. So in principle, although we could get helium white dwarf, we shouldn't get them because it takes too long for such stars to actually form helium white dwarf. However, we do see helium white dwarf, okay, when we look at the sky. How is that? The idea is the following. You have a more massive white star that should have produced, for example, carbon oxygen white dwarf, but then it has a companion, okay? So it starts burning, it produces a helium core. But then the companion star, it's close enough and it takes some of the material, okay? It strips the material. So now you have this helium core, but you have much less material. This less material, it cannot burn the helium anymore, and you form just a helium white dwarf. So helium white dwarfs form from more massive stars that were stripped of the envelope. So that's the idea of how to form a helium white dwarf. As turns out, so that was the main kind of the regular thing that people discuss about helium white dwarfs. What people did not mention too much is that, although of course Russian did it first in the 80s, okay, is people already suggested you could also have a hybrid white dwarf, okay? Hybrid white dwarf, what do I mean by that? It depends when you strip the star. If you have a bit more massive star or you strip it a bit later, the helium can actually burn a bit to carbon oxygen, okay? So you have a carbon oxygen core, but you strip the rest, so you're still left with a lot of helium that wasn't burned. So you have a strange hybrid case. You have a carbon oxygen core. On top of that, you have a very massive shell of helium. And I already told you that helium is very important in principle, because helium can detonate much easier. And so that's going to play an important role in the model that I'm going to suggest as a model for type-1 supernova. I won't go into that. You can actually we actually model the formation of these helium white dwarfs and the hybrid white dwarf and various different types of modeling. They are all quite consistent, and we have actually very specific characteristics of this white dwarf from a consistent stellar evolution model. You can even look on how these white dwarfs should look like. It's not very easy to find them. First of all, because they have to be in binaries. So I told you need a companion to strip away the mass in order to get it. So they're only found in binaries, so they're relatively rare. They're not rare in binary white dwarfs, but they are rare in general. Okay? So, and it's not easy to actually identify them because in order to identify them, you need to know what's the mass and the radius. You usually don't know both of these elements. You need to do some transit observation. It's very difficult to actually identify these white dwarfs exactly, but in principle, people actually have some already have some candidates for these white dwarfs, and as it turned out, they actually have quite a few compared to the fraction that we should have expected. Okay, so now I told you that we have not just helium white dwarfs, carbon oxygen, and oxygen neon, but we also have these hybrid white dwarfs, which turns out are between 0.4 and 0.7 solar masses. So kind of in between, as expected, between helium and carbon oxygen white dwarf, they kind of have overlap in terms of the mass. Okay, so why is this all important? Because I already told you that all of these models of these different white dwarfs did not work. But if you now have another new type of white dwarf, you have all these other possibilities of combination. As simple as that. So once you have a new combination, you should try and explore them, see what happens when these white dwarfs merge with this new type of hybrid white dwarfs. As it turns out, this is what we suggest. This makes all of the difference. Why is that? First of all, because in terms of if I suggest that this could actually explain supernovae, I need to have enough of them. If I don't have enough of them, it doesn't matter if they explode or not, we never get what we want. If you actually do this population synthesis, right, to kind of model many stars and binaries, see how much we expect to see, even what we know from the astrophysical observations, turns out that about 25% of all cases where we have two white dwarfs that should merge, okay, 25% of them include this one hybrid white dwarf. Now, we already know from the observation, actually mostly from Danny, that we need about 50% of all mergers of white dwarfs in order to explain all the type-1 supernovae. This means that in principle, at least, we have more than enough. Okay, even if not all of them explode, we have enough of them in principle to explain supernovae. So that's the first kind of very simple basic test. Okay, but that's not exploded. That's already in principle if they explode. What do you need to do in order to check whether they explode? Well, you need to model all this evolution of stars, make a hybrid white dwarf in your stellar evolution. Then you need to actually merge them in hydrodynamical simulation, actually really look on simulation. These are very complex simulations because they include both hydrodynamics, gravity, nucleosynthesis, thermonuclear evolution, radiative transfer, shock dynamics, equation of states, all of these come together. Okay? So it's pretty complicated. You need to do it step by step. So you do model this basic simulation, but these basic simulations usually they are very expensive. They not always include all the elements like the thermonuclear aspect. So then you can model them. This is a 3D model. You can model them in simpler models, but they do include all the thermonuclear aspects. Tell you a bit about that. You can explode them if they explode, or check whether they actually get a detonation if they explode. If it does, you can see what kind of composition it produces. You can actually post-process it, so-called, look at the detailed composition that you get in the explosion. Then you do a radiative transfer model. You see all the photons that form during the explosion and how they kind of go and radiate through this whole material. What kind of spectra would they show in the end to observer very far away? What kind of light curve? These are actually observable. You need to go not a simulation into the full observable. So we need to actually model that. Once we have that, after all this, we can actually compare directly to observations. So all this took at least 3-4 years of actually getting all this together in line, all the ducks in line to actually get all the things. And of course, it's really rewarding to see in the end that you do simulation and you get something which actually looks like a supernova. So that was one of the fun stuff like 2 or 3 years ago when we first got our actual observation. So now the question, of course, does it really work? So the idea is that since these are very expensive simulations, it's very difficult to do them in 3D. Okay, and I'll get to 3D, but before that, what we do is the following. In our models, we have a CO white dwarf, and you have this hybrid white dwarf. They come close together. The hybrid white dwarf is less massive, and it's a larger radius. And it's actually because of tidal interaction, okay, like the Earth-Moon tidal interaction, it's kind of shredded apart, okay, disrupted, and it forms this material that forms a disk, of accretion disk around the white dwarf. Why is that good for us in terms of computation? Because once it forms a disk, it has a symmetry, okay? It's just a disk, a symmetry. Then you can go to do effectively 2D simulation. You use this symmetry of the simulation, symmetry of the actual physical aspect, and you can actually model this in effectively 2D. 3D or 2D is a symmetry. So this is what we do here. What you can see here, for example, is you have this white dwarf on the left, and this is actually a cut of the disk. It's a very, very kind of large disk, you can see. Material starts accreting in. This material now includes both helium and carbon oxygen. So this is a hybrid, includes both of them. The helium is easy to ignite. So that ignites after it kind of goes to accrete onto white dwarf, high temperature density, it ignites from this first relatively small but still quite strong helium detonation explosion. This compresses the center, and then you have a second explosion now for the CO white dwarf. So in that sense, it's some sense related to this double detonation, but in a different way. It's a different type of white dwarf. It's this disk that is accreted, and in all these other models, people suggested it actually never really exploded. It didn't have actually strong enough detonations of the helium to really do enough compression. Why do we have that? Because we have much more helium, because we have this hybrid white dwarf, and you have all this material for the full material of the white dwarf around. So you have a lot to burn. So this is why visibly you can get it. And this is the amount of nickel that you get, nickel 56 inside the element. First, in the first explosion, you get a very little. This is the helium detonation. And then it leads to a second detonation, you form a lot more, about 0.6 solar mass of nickel, which is what is inferred for the amount of nickel that you have in type 1. So in principle, it looks like it explodes. Okay? I won't go into that, but in principle, you can actually show that it compresses things enough to actually form a lot of nickel. You can ask me more about that if I have the time. Does it look like a supernova? Okay, does it really look like a duck? So it turns out it does. If you actually now compare this observation, we look on the various type of the light curves, how the light curve rises and go down, or the really detailed spectrum, okay, how the spectrum looks like. These are actually consistent. We have this model, for example, one of the best observed supernova in this case, supernova 2011 Fe. You actually get very, very good consistency. If you actually saw other models, you will realize that these are very, very good. If you know, and these are actually not fitted. You just do a grid of model, and we didn't try to fit a specific supernova. We just did try to this model. More than that, you actually find out that if you actually on the rates of the supernovae or the delay time distribution, I have better slide for that. Okay, I'll get to that in a second. You can also look on which places do they cover in this kind of characteristic diagram of the time scale and luminosity of supernovae. So this is what we saw, and we have a zoom in, and we can see that all the models until now what I show here is not just an example. These are all the models people actually did a full simulation with, and they show the light curve, etc. So each one of them just represents one simulation, and these are more or less the region they showed. Some of them are here, a few of them in the most luminous ones, and some here. We actually, because we did this 2D simulation, we could actually do a much larger phase space and check these, and we get something like that. We get most of them are here, but also some in the other places. As it turns out, it really depends on the radiative transfer model that you do. Now we know that with the radiative transfer that are more realistic, you can actually smear them and actually make more closely to the Phillips simulation. On the other hand, we never actually get to the most luminous ones that people did simulate that I told you are coming from these very massive white dwarf emerge. So we can actually potentially extend most of the phase space of this standard supernovae, and maybe I'll have time to talk about the other one, but not the most luminous one. But as it turns out, most of the supernovae, this is biased here, but most of the supernovae are actually not the most luminous ones. See here. Sorry.
So now.
Wrong one. Okay, doesn't show it. That's good. Okay, we can look at the daytime distribution. Now we run this population synthesis, see in the models how many supernovae do we get and when do they explode. Since we know we have a full phase space of which of our cases we try different masses of white dwarfs, different combination, we know which one of them explode and which one do not. And not all of them explode. Depends really on the mass. You need enough mass in the two white dwarfs and specific relation for them to explode. So we include only those in the cases that we actually explode, and we can actually do this diagram. And it turns out it actually is consistent with, potentially consistent, depends of course on various assumptions, but it's overall very consistent with what we see. And there are actually different types of measurements. Danny can tell you more about that, about the delay time distribution, when do supernovae explode and how many of them. But it's actually much better in almost, it's the first model that predicts this whole thing, really, from actual simulation. People suggested one explosion, then extrapolated to different explosions. We actually did the whole phase space and put that into the projection synthesis. We are able to reproduce this. The most luminous supernova I told you about, these are coming from other models, but they consist about a third of supernovae are coming from those massive white dwarfs, and about 2/3 or so are potentially coming from our model. Of course, I have many caveats which I tell you in the end. Now I try to tell you that everything works and everything is nice. Obviously, in physics, it's not always like this. So what are the main open questions? So in principle, what I told you, I have a working model for supernovae. I can explode supernovae which look like type of supernova. Their demographics look like the spectra. Both the basic properties and both the general properties are generally consistent. We still have a long, long way to actually really say this is the right model. And some of these related to all the kind of simplified assumptions we did. I told you we did these 2D models, but when you have two white dwarfs come together, this is a 3D complicated explosion. And before they actually come together and one of them disrupts, they can already transfer material from one to another. I even told you that one of the models suggested you transfer material, you explode the white dwarf before the second one even disrupts and make this whole disk. So maybe even our initial conditions are wrong. So we need to check this. Whether our shock is strong enough to really compress the central part, it's an open question because when you do 2D simulations, again, we induce a symmetry which doesn't necessarily exist at the same level as 3D. So 2D, no, we put very specific assumptions that would actually help us in a sense compressing or detonate much stronger. So it really depends on the 3D. We have other types of supernovae which we cannot explain. We can't explain many of these various types of supernovae. I didn't tell you too much about it. If I have the time, I'll do that. But some of them are not. Some we suggest we can actually explain them, but from a different model. So both of these first things do require 3D simulation. The other ones are maybe coming from a different model, not a double degenerate, but single degenerate. How much time do I have? That's it? More or less. Okay, good. So I'll try to just close down with that. And I'll just give you the kind of the final cut of what we're actually doing right now, what we just published in the last year or so. And what we started doing is to do 3D models. These are very expensive, months of thousands of CPU or millions of CPU actually hours. And these are much more complicated. And you can do two white dwarfs, and you see how they start coming together. One of them start to transfer material. What you see here is the detonation of the helium before the second one is even disrupted. So this is what I was worried about. If you have a detonation even before we actually disrupt the white dwarf. And it starts doing that. And what happens then? Well, if I'll be able to do that. Okay. Can you see that? Okay. So what you see is the simulations. These are two white dwarfs coming together. you can see them start to transfer material. Now it slows down because all this nuclear aspects are becoming important, and you have the helium, which is going to detonate very soon. So you see this helium detonation. Then the question whether this is the helium detonation, okay? But you see that this helium detonation, okay, in this case, it did not actually explode the star itself. Star is still there. What will happen is actually afterward disrupted and started to form this accretion disk. So we did have a helium detonation even before the formation of the disk, which was dangerous for us in some sense, but it did not actually produce a normal supernova. It just produced a very extremely faint thing, not even a supernova, but you actually formed in the end this disk that we actually started in our simulation. Whether the disk is good enough compared to our 2D simulation, we need to compare, but this is the first question, can they actually be disrupted, not produce a supernova from a different type of process? It seems like we can actually produce this. The question then is whether we actually produce later on the second explosion. We are just in the midst of actually trying to explore whether this happens also in 3D. Okay, so we go back here. Okay. Here we actually have another interesting aspect, but I need to finish, so I'll finish with that. I just mentioned that you can actually expand all the various ones. I told you in some cases it doesn't explode, it actually explodes partially. Turns out this kind of partial explosion would potentially explain all these strange, peculiar supernovae, the other types of supernovae. So we not only explain normal supernovae, but now we understand the relation between them and the other types and why do one type form and not the other, and all these relations. So it's the first time we actually not only produce normal monads, but all these various types. Not completely all of them. I told you some of them do come from probably massive CO growth that merge together, but at least a significant part of them. So in principle, we might be able to explain all of these data. So I'll just go to the end and not talk about all the peculiar supernovae. And those, okay, and I'll summarize. So what I try to tell you is this whole story. Okay? We have a disruption of hybrid Helium-CO growth by carbon oxygen growth. If they come together through the gravitational wave, it disrupts, forms a disk. The disk material accretes on the white dwarf. You have a lot of helium and carbon oxygen there. Helium is easily detonated. It detonates, produces explosion that burns also part of the carbon oxygen, compresses the white dwarf, and produces a second detonation, the carbon oxygen detonation, that produces something which actually looks like a normal type 1A supernova. So, and produce a consistent model for type 1A supernova. So, and it can also explain all these various types of a hybrid or of strained supernovae. For example, let's say you accrete, you form this helium detonation, but it doesn't compress enough the white dwarf. For example, the white dwarf is too low mass, it doesn't explode. So you have only the explosion, the first explosion. It produces about 0.05 solar mass of nickel or even less. In this case, you get extremely faint supernova, which in principle is bad, but actually it's good because we do have some of these subtypes which are very peculiar and faint. They also produce less nickel and much more intermediate elements. So that's actually consistent with those supernovae. So we can also explain those cases. So with that, I'll finish and try to say that this is what we're working on, trying to really explain where the origin of all the elements are in this type 1A supernova. Thank you.
Are there enough white dwarfs of the right kind to produce the number of supernovae that is observed?
Yes, so this is what I told you. This was more or less the first thing I showed you, is to try to model this on how many white dwarfs do we have like this. And I showed you that we have about 25% of all the white dwarfs that merge in the models include these hybrid white dwarfs. So in the models which include the whole stellar evolution. So yes, we have enough of them because we need only 50%, we have 25%. So in principle, we have enough of them. Observationally, it's very difficult to identify them, so we're not sure. But among the 7 cases where in principle you could do this measurement, 2 of them were potentially hybrid white dwarf, which is consistent with the fraction that we calculated. But again, these are very, very partial and small statistics, so I wouldn't trust that yet. But in principle, on the models certainly say that we do have enough. The observation, it's just difficult to know. In principle, what we see right now is consistent, but I wouldn't take this as evidence at this point.
So in the movie you showed in the end with the new work with Buckmore, so you get your disk, but then what happens? You need just a few more seconds of real time to see if it explodes or not.
Okay, good. That's a very nice question. So what happens from the disk? In order for the disk to actually accrete all the way through, you need somehow to actually get viscosity, to make material actually go around. In the 2 simulation, this was usually people do it, it's very difficult to actually model viscosity. First, we don't really understand it very well in astrophysics. And secondly, as usually, you know what you ask in the end of this in astrophysics. Every time you need to ask in the end of the question, what about the magnetic field, right? So this is true in astrophysics, this probably in some other fields. So yes, the magnetic fields are very important to produce this viscosity, but it's very difficult to simulate them. And it starts from a kind of fluctuation of modes that actually grow. And you actually cannot resolve the smallest mode that actually grow in magnetic fields, even if you put magnetic fields. What did we happen there? So we actually did put magnetic fields, and they grew very, very fast, but not enough to actually produce viscosity. Now, we know we have viscosity, okay? We know from observation of many things. So certainly we didn't catch it. In other models, for example, people did on small shearing blocks, or you can actually resolve small scales, then they can see these small modes that grow. We don't have it in global simulation. So we effectively don't have viscosity in these 3D models. So what are we going to do? Two things. One is actually map back the 3D simulation to just alpha viscosity, to put the viscosity by hand. So that's the next step. The other hand is actually increase the magnetic fields artificially, because we know they should happen there. We just cannot resolve the smallest mode, and then continue with this and then get a consistent this viscosity. So these are the next steps. These are expensive. Already see this there, but this is more or less the state of the art. So I'm really showing you kind of the category we are. I do hope that we have the question. The other question is whether we have enough helium, because some of the helium did burn all the way. Not all of it was left like we assumed the 2D model. Do we still have enough helium? That's another question. So we have seen certainly an open question. That's actually very important. But it's very clear that they're going to play an extremely important part in all of this. Whether they can explore all these models like we see in the 2D, I'm not yet sure. But I think we have a lot of potential already there. And for the experts, we actually also check the D6 models. They do not work in our 3D models, only from if you need 1.05 solar mass of zero white dwarf. If below that they don't work, so they cannot explain all this. But anyway, sorry, that was just for the experts. The problem is that this explosion happened on a second time scale. What we see, tens of days later. Okay, we don't see directly the explosion. But what we do see is that the first explosion does produce different elements than the second one. And so the mix in principle should tell us something about that. I was asked about the sphericity. When you have this model, the first, you might actually produce some non-asymmetry because, for example, you have a creature in this, so it's not like spherical. You have some material. When you produce a second explosion in the center of the white dwarf, that's quite spherical. But the first one is kind of less spherical, so you might actually see some evidence for that. So we try to look for these things. In principle, you can indirectly look at it. You cannot see directly the explosion itself. It's actually, it's inside a huge amount of material. The light doesn't even go through at this point. Okay, so you need to wait until it comes out to actually see. So you don't really see directly. Indirectly, in principle, yes, all of these things. And for this, again, you need 3D in order to get all the structure, and then the polarization, which is extremely difficult to do, both observation and simulation. So as you can see, there are many, many, many steps, but yes, in principle, this is something that can be checked observationally in some sense.
Yeah, you have a mix of models. Using these models to do two things: rates and also delay time distribution. If you were to take, I don't know, if you take your data, the observations, divide them into two categories, types of galaxies by some category, you get the same solution always, or dependence on how you actually select.
So that's actually a question in some sense for Danny about the observation side of the things, about the data and distribution.
Well, both observational.
Yeah, so on the observation side, you need to actually check, for each galaxy has a different star formation history, and you need to account for that in order to actually get, in a sense, the green function that I told you about. So this is some of the things, for example, that Danny does. On the simulation side, we do a population system. We run all the binary stars that we're supposed to have according to the mass function, what we know from observation. Then we run them and see which one of them from binary white dwarfs, which then merge them. And then we know, of course, the delay time distribution. We know when they form.
You have to use the same population synthesis for the entire universe.
Yes. But we also, I show you that I didn't go into that, but we also check different metallicities, of course, which affect these things. So yes, in principle, you need to account also for the distribution, and we can do that. It's more complex. You need to account for the different distribution of metallicity and different time scale during the universe. So we're not at that point level, but we actually can show for specific models with different specific metallicity. Then it's just a mix of all the components. You just weight these kind of green function, right, about the metallicities and all this, so you can get the general model. So this is not that difficult, but you need, we're still far from saying that we understand all the other things, so we didn't go into that level of detail because there are so many uncertainties which are much bigger. It's no sense of going this point to get to this level. We did show that, as you can see, to a factor of really small number, of factor of 2, we actually consistent with this. That's already extremely good. Whether we can do the complex things, I do that once I have a 3D model, for example. Oh, I can do that before, it's easy. I just want to trust it before I know what really exposed in the 3D. But certainly that's something that is part of this course.
Oh, discuss with you later.
May I ask a question? Yeah. To make a breakthrough, what do you need? A superpower computer or a new understanding better physics of interaction?
So as always in theory, not always, but in this case, it's a very complex combination of things. Computation power is extremely important in order for them to run really a grid of things or get to high resolution. So that's one thing. The other thing is actually the physics, because the part of the problem is that you have different scales. White dwarf size like 10,000 kilometers. The actual detonation happens on a centimeter size. Okay, we don't want to resolve really detonation. We have so-called the subgrid models. You can resolve up to about a kilometer or a few kilometers. Below that, what you say, we know from very resolved simulations, different ones, just really resolve at small scale. We know the physics from there. We introduce it into the global model. But obviously, the connection is there are a lot of assumptions going on there. So in that sense, yeah, we do need to understand better the physics and the relation to really do it, know how to do it completely correctly. So it's both the computation, because that gets you resolve higher, but that might not be enough. You need to also go from the theory side to really understand the relation at different scales and different aspects. And I just mentioned one of them, there are many other aspects. So additive transfer is complex. All these things involve both the physics and the computation. So
Yes, but what is more important? If today you will get a computer which is 100 times more power, you believe it will work?
Yeah, so right now I'm focused on the computation side. 3D models require a lot of computation. So right now, and that goes very fast. It gets better, much faster than the theory goes. So it's easier to go this point, this direction. But as I said, for example, introducing this new white dwarf, that's a basic physical element. And that was much more critical than any kind of simulation. Because it doesn't matter which kind of simulations they didn't work until I introduced this white dwarf. Or this is what I claim. Time will tell whether I was right or not.
Okay. Thank you very much.
Thank you very much.